হ্যালো শুভম।
ভাই, সব ঠিকঠাক তো?
হ্যাঁ, সব ঠিকঠাক। হ্যালো স্যার।
হ্যাঁ, বলো। হুম।
হ্যাঁ, আপনি হ্যালো বলে মানে শোনা
হ্যাঁ,
যাচ্ছে ঠিকঠাক।
হ্যাঁ, হ্যাঁ, শোনা যাচ্ছে। এটাকে যদি একটু বাড়াতে চাই তাহলে কি করতে হবে বলতো?
গুড আফটারনুন প্রিয়ব্রত দা। হ্যাঁ শুভম, গুড আফটারনুন।
হ্যালো।
হ্যাঁ শুভম।
হ্যাঁ, হাই।
হ্যাঁ হাই,
প্রিয়ব্রত,
ভালো
তোমার
আছিস?
মাইকটা হ্যাঁ দিদি
একটু
চলে
সমস্যা
যাচ্ছে।
করছে। হ্যাঁ হ্যাঁ হ্যাঁ, প্রিয়ব্রতদার মাইকটা একটু অস্পষ্ট আসছে।
মানে শোনা যাচ্ছে কিন্তু মাফেলড আসছে ভয়েসটা, তুমি একটু ঠিক করো। Third batsman arrived.
গুড আফটারনুন রঞ্জন। স্যারও এসে গেছেন, ওআইসি স্যার এসে গেছেন, এইচওডি স্যারও আছেন।
Good afternoon, all.
হ্যাঁ, গুড আফটারনুন।
Good afternoon, everyone.
গুড আফটারনুন।
একই রকমের। হুম। হ্যাঁ তখনই তো তোমায় যেটা বলছিলাম।
গুড আফটারনুন স্যার।
Good afternoon, sir.
Good afternoon.
How are you, sir?
Fine. Thank you.
Okay, sir. I'm really glad to see you. Really glad.
Yeah, it is very interesting workshop. Actually, I just now came from Chennai. So
Okay.
immediately joined. I could able to join the 3:35.
Okay, sir. Okay, sir. Thank you.
It's nice. Yeah.
Good afternoon, Shumanto. Good afternoon, Dr. Misra.
How are you? I hope fine.
Yes, sir. Yes, sir. Very glad to see you
No, okay.
present. We are really feel happy that both of you and Nagendra sir are present here today.
Okay. Nagendra sir.
Thank you, sir. Thank you.
Good afternoon, Professor Nagendra.
Good afternoon, sir.
Good afternoon.
Good afternoon. How are you, sir?
I'm very glad to meet you.
So, how are you, sir?
Okay. You are in Karnataka or in Chennai?
Yeah, just now I came.
Okay.
Just 5 minutes back I came from Chennai.
Okay. So what is the time? 4 p.m. for us?
Sir?
4 p.m.
Yes,
for
sir.
us.
Yes, sir. We are just going to start.
Okay.
Yeah.
Okay, sir.
Okay.
So, I'm asking to my HOD sir. Sir, should we start? It's 4 sharp.
Shekhar Shah. Okay.
Sir?
Sir, madam?
No, sir. Thank you, sir. I'm asking actually my HOD. Ashish sir.
HOD sir. Okay.
I'm watching.
Okay, so our HOD just left due to some internet issues. He's just joining. After that, we will start. Okay, I think Dr. Maji has joined, so we can start now. Good afternoon, everybody. Greetings from Bengal. Department of Geology, Kobi Jagudram Rai Government General Degree College, Bankura of West Bengal, India. Welcome you all. Today we have been assembled here on this virtual platform to be a part of the one-day international online workshop on fundamentals of planetary science, methods and scopes. Myself, Nivedita Chakraborty, accompanied by my departmental colleague, Ms. Indrani Mondol, being the organizing secretaries of this workshop, like to now invite our respected head of the department and the IQAC coordinator of our college, Dr. Ashish Kumar Maji, for the welcome address. Sir, please.
Hello, am I audible?
Sir.
Yes, sir.
A very good afternoon to everybody. I feel privileged to extend warm welcome to all of you to the one-day international workshop on fundamental of planetary science, methods and scopes. During the fag end of the pandemic period, we have been virtually clubbed together to attend this workshop instead of gathering under the same roof in our college. With time, the planetary science has become increasingly important, especially to combat the daunting challenges in finding out the natural processes in the extraterrestrial domain. Thus, we should be acquainted with the recent development in different fields of planetary science. The present workshop focuses modern trends on some of the important topics of planetary science. This will be elaborately discussed by our three eminent resource persons from different premier institutions all around the globe. I am sure that this workshop will significantly enrich the knowledge about the planetary science to students, researchers, faculty members and all nature lovers. Enjoy the workshop with fruitful discussion. With these few words, I remain here today. Thank you. The rest of the program will be conducted by Dr. Nivedita Chakraborty and Professor Indrani Mondal, Assistant Professors of Geology, this college. Dr. Chakraborty, please.
Thank you very much, sir, for the warm welcome, your thoughtful words and significant remarks. Now, I would like to invite our Honorable Officer in Charge, Professor Alok Kumar Dash, for the inaugural address of this event. Sir, please.
Am I audible?
Yes, sir, fine.
Good afternoon, everyone. It is my great honor and pleasure to inaugurate the one-day international online workshop on fundamentals of planetary science, methods and scopes, organized by the Department of Geology, Kobi Jagudram Rai Government General Degree College, Mejia, Bankura, West Bengal. On behalf of the college, once again I welcome you all. In the past, scientists had only one planet to study in detail, that is our Earth, the only place where life demonstrably exists and thrives. Nowadays, planetary scientists can apply their knowledge to the whole solar system and to hundreds of worlds around other stars. Consequently, in recent years, planetary science has seen a tremendous growth in new knowledges such as discoveries on the surface of Mars, suggesting to an early warm way to climate and perhaps conditions under which life could have emerged and so on. This present online workshop has been framed to provide a state-of-the-art knowledge on various research methods and future research scopes of the planetary science by the eminent resource persons. I feel that it would have been better if we could arrange such sort of discussion by inviting the eminent resource persons and audiences in the college. Anyway, this online workshop will provide an excellent opportunity for the participants to explore and share the knowledge on latest advancements in planetary science. I wish a grand success of the workshop. Thank you. Thank you once again. Now over to Dr. Nivedita Chakraborty. Please.
Thank you so much, sir, for your meaningful address, encouraging words, and for being with us. We will be obliged if you can stay with us for the rest of our program amidst your busy schedule. Thank you very much. Now we will proceed to the main segment of our event. Good afternoon to all of you once again. On behalf of Department of Geology, KJR GGTC, I would like to declare that the one-day international online workshop on fundamentals of planetary science, methods and scopes is now open. Respected officer in charge, Professor Alok Kumar Dash, respectable our head of the department, Dr. Ashish Kumar Majhi, honorable resource persons of this workshop, Dr. Priyobroto Dash, research investigator of astrobiology, team lead of planetary sciences of Supernova Private Limited, and visiting researcher of PRL ISRO, Dr. Ranjan Sarkar, planetary scientist and postdoctoral fellow in Max Planck Institute for Solar System Research, Göttingen, Germany, and Mr. Shubham Sarkar, GST Inspire Fellow at Space Application Center, ISRO, Ahmedabad. Our distinguished guests and participations from different academic institutions, government as well as private organizations all over the country, my senior and junior colleagues, dear friends, the non-teaching members of my college, my students, and all the other persons who have taken interest in this program, especially Professor B. Mishra, Professor Nagendra, Professor Mahapatra. My sincere greetings and warm regards to all of you. It is my immense pleasure to welcome you all in this event. Imagining life on other planets and their moons is a fascinating area of research. Even in the recent past, science fiction writers and Hollywood directors indulged in fantasies of little green men and triffids. Now, day by day, astrobiology and planetary science are growing as serious field of research work. The planets discovered till date are mostly uninhabitable for humans, that they are either too close or to their star or enormous gas giants, if I am not wrong. Our resource person will speak on this even better to me, of course. Science is now developing to the direction where we may be able to detect which planets have liquid water. Planetary science missions and research inform us about our neighborhood and our own origin and evolution, and they are necessary precursors to the expansion of humanity beyond the Earth. In the future, humans maybe will return to the Moon, Mars, or other solar system bodies to explore them, after they have been investigated and understood using robotic missions. However, at present, the expansive nature of modern science, research demands a more comprehensive approach involving ground-based plus space-based programs and observational facilities. Importance of evolving stronger student training programs and human research generation and encouraging students or scholars to take up the space science research as a career should be facilitated. Keeping in this view, Department of Geology, KJR-GGC has taken up this initiative of arranging a brief workshop on the fundamentals of planetary science, which we hope will be useful to especially the students and early researchers for learning the basics of this growing and promising field of research. The workshop will also enable the participants to interact with the experts in this field. It is our privilege to have three distinguished planetary scientists as our resource persons during this one-day workshop. All of them are very special and specialized in their own fields. Now I would like to request Indrani, my companion, to introduce our resource persons to the audience. Indrani, over to you.
Thank you, Nivedita Di, for giving me the opportunity to introduce our resource persons. Today, we are thankful to have with us three promising researchers in the field of Martian geology as well as the planetary science, Dr. Priyabrata Das, Dr. Ranjan Sarkar and Mr. Shubham Sarkar. We are fortunate enough to get this opportunity to hear about such an highly demandable topic of this century. It's my pleasure to introduce Dr. Priyabrata Das, one of the most prominent Earth and planetary geoscientists, currently serving as a research investigator, astrobiology and team lead planetary science of Space Nova Private Limited and visiting researcher of PRL Ahmedabad ISRO. After completion of graduation in geology honors from TDB College Raniganj, Dr. Das did his post-graduation in applied geology from Presidency University, Kolkata, and received a doctoral degree in Earth Science Precambrian Geology from Hiroshima University, Japan. Thereafter, he continued his research work at various Indian institutes like Jadavpur University, Kolkata, Physical Research Laboratory, ISRO, Ahmedabad, and Manipal Academy of Higher Education, Manipal. Besides academics, he also worked in mining and mineral industry and has consulting experience in civil engineering and geotechnical sectors. He has a handsome publication list in various peer-reviewed journals, including Precambrian Research, Meteoritics and Planetary Science, and many more. His research work has involved understanding the early geologic evolution, surface processes, habitability of the Earth and Mars using the geological, geochemical and planetary mission instrument techniques. He has expertization on the early geologic evolution, climate and habitability of the planet Mars. He will also focus on the career potential of planetary geoscience and the upcoming applications of space science and technology in the society, research and education sector, science, communications and many more. Today, he will talk on a topic entitled as Why Do We Explore the Planets? The Geological Perspective. And the next resource person is another distinguished planetary scientist, Dr. Ranjan Sarkar, currently working as a postdoctoral fellow at Max Planck Institute for Solar System Research, Göttingen, Germany. Dr. Sarkar did his BSc honors from TDB College, Raniganj, completed his master's degree in geology and PhD in Martian geology, both from IIT Mumbai. Thereafter, he also worked as a research faculty of Center for Astrobiology, Amity University, Mumbai. His research work has involved understanding the early geologic evolutions of Mars and solar system objectives using the planetary remote sensing technique. His present research, however, mostly focused on the understanding the geological evolution and mineral mapping of asteroid series using the NASA's Dawn mission data. He has presented his research work at various international and conferences, published research articles in various national and international journals. He will deliver a lecture on Geology of Planetary Bodies, an overview of orbital explorations. Our third resource person is Mr. Shubham Sarkar, one of the most promising future planetary scientists in the field of Martian geology. Currently, he is the DST Inspire Fellow at Space Application Center, ISRO, Ahmedabad, pursuing PhD in Planetary Geology from Kutch University. He is in an advanced stage of his PhD degree, will submitted his thesis soon. He has expertise in planetary geology, planetary mineralogy, geochemistry, reflectance spectroscopy, Mars geology, and Mars analog. He did his BSc and MSc both from Presidency University, Kolkata. Thereafter, he joined SAC, ISRO, Ahmedabad as DST Inspired Research Fellow. He has more than 12 research publications in multiple journals and conferences like Minerals, Geochemistry, Planetary and Space Science, LPSC, etc. The lecture entitled as Exploring Mars with Perseverance rover will be delivered by Mr. Shubham Sarkar. This is a very short introduction compared to their achievement. We cordially invite all the three resource persons to our one-day international workshop and hope we will surely be enriched after this session. Now we'd like to hand over my colleague Dr. Nivedita Chakraborty to continue this session. Nivedita Di, please. Please unmute Nivedita Di.
I'm so sorry. Thank you, Indrani, for such a nice introduction of our resource person. We are really pleased to welcome them in our workshop, and thank you very much to them for their support. The lectures delivered by them will cover some unique perspectives and recent updates on planetary science. I believe the vividness of their lessons will not only encourage the students and scholars, but also to the non-geology persons and common people. We are overwhelmed with spontaneous response of students, both UG and PG level, research scholars, teachers, professionals from different state and central universities, different government organizations and private companies. We are delighted to share with you that we have total around 150 registered participants from different institutes all over our country, including all the geology department of all the government and non-government college and universities of our state, and University of Delhi, Hansraj College of Delhi, BHU, ISRO, IIRS, Dehradun, Keynes Energy, GSI, and many more institutions from Kerala, Pondicherry, and Dhanbad, Gujarat, etc. And few were from some universities of Nigeria as well. So thank you so much to all of you for showing interest in this event. I hope you will enjoy to learn, and this workshop will be a memorable educational event for all of us. I cordially welcome you all once again to this workshop and hope that you will all have a great time ahead. We truly value your participation and support. Thank you so much for joining us. Thank you for your kind attention and participation. Thank you all. Now I would like to move in the main segment of our event, that is the technical session. In this session, we will have 3 lectures by 3 resource persons, as Indrani already mentioned, and there will be 2 interactive sessions, one after the second lecture and the third one will be after the third lecture. Our first speaker will be Dr. Priyobroto Dash. His lecture will focus on the fundamental areas of planetary science, and he will direct and coordinate the workshop after his lecture as well. So I would like to invite Dr. Dash. Now the virtual dais is yours. Dr. Dash.
Hello. Thanks, Nivedita, for such a wonderful introduction.
No, it's our pleasure. It's our pleasure.
I'm sure Shubham and Ranjan also will be as glad.
Of course, we are actually eager to.
We all belong to Bengal graduation and post-graduation here. So, and it's really nice for us to do in Europe. Always appreciate this kind of thing. So without wasting any time, I'll just start my talk because it's already 4:24. So Today's topic is why we need to explore planets from a geological perspective at present. Because planetary science is a very huge and vast program of research, and people from all over the world, from different backgrounds, can participate to understand the planetary systems and planetary bodies. But what we geologists can contribute on this understanding is to understand this thing
So
better.
thus, it is not audible.
So, hello, am I audible?
It is not audible.
Hello, am I audible now? Hello?
Yes, yes, yes.
Yeah,
No.
it's better now.
Better now, no? Okay.
Yeah.
So, what is planetary science actually? Planetary science is the scientific study of a planetary system of different celestial bodies. In one single sentence, we can say the study of planetary systems. And it is a very interactive, interdisciplinary field of research, and from different backgrounds, from atmospheric science, from astronomy, geology, space physics, then biology and chemistry, and all across other disciplines can also participate to understand these planetary systems. Okay, so but actually, who can do this type of science? It's very interesting thing. Actually, everyone can do this science because the data is available for the they have a cyclicity. Okay, one is thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, thin lamina, and thick lamina. So there is a cyclicity in this outflow. And how the cyclicity, cyclicity can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, thin lamina, and thick lamina. So there is cyclicity in this outflow. And how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, and thick lamina. So there is cyclicity in this outflow. And how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, thick lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick lamina, then thin lamina, and thick lamina. So there is cyclicity and how the cyclicity, can be developed, that is a big question. And we are working on this part. Our initial data has been published in an abstract format containing the cyclicity. And so the thick lamina, then some thin lamina, then again some thick. Hello.
It's okay now, Priyoda. Carry on. Please carry on.
So the last point is that I mentioned here that so we have this kind of image in the 70s, it's a Voyager image.
Okay, now it's clear. Now I think it's stable.
Oh, okay, that's why I played the video one. So the video has some noise. That's why we got it. So,
Carry on, yeah.
yeah. So this is the 70s, 1970s image of Mars, and now you can see this is the today understanding how water, the compound variance of water on the past, Martian past, it is about the past. Okay. And also in 2020, we got the compound evidence of this organic, complex organic molecule. So what next? What next? We get any signature of this type of structure as a like stomatolyte or something else, because Mars also has a thermal deposit that Shivam Sarkar will explain. And that's why NASA has planned its ongoing mission, the first year mission on the Zero Crater. Because the Zero Crater has a perfect place where actually this kind of light form can be feasible. So, and over to Ranjan Sarkar, we will discuss about the next orbital remote sensing and how we can use orbital remote sensing to understand the celestial bodies and planets. So, thank you. Hello, Ranjan.
Hello, yeah.
Hi, can you continue?
Am I audible? Hello?
Yeah, fine. You can carry on, Ranjana.
Okay, yeah. So I will start sharing my screen.
Yeah, perfect.
Is this visible to everyone?
Yeah, it's visible.
Okay. So good afternoon to everyone, and I am very grateful to you for giving me this opportunity to share my excitement and curiosity that I have for planetary sciences. And I hope that many of you will also share the same excitement along with me. And maybe this will guide you to become like a scientist in the field of in this field, or maybe even if you don't want to venture into the planetary science field, you could use these same concepts and knowledge to do terrestrial geosciences also as well. So I'll proceed with the presentation now. Here is an outline of what I'll be talking about today. So I have organized this presentation as follows. First, we will be looking at the orbital remote sensing. First, we'll be looking at what remote sensing is, and followed by some of the most common techniques and methods that we apply to analyze and interpret the satellite data. These include doing some photogeologic interpretations that require elevation or topographic information. We'll also look at how we can derive the mineralogical or compositional information from satellite data sets. And also there are lots and lots of other techniques of remote sensing which I will not be touching upon in this presentation, but I will give you I'll state the names or the domains where those are carried out. Coming to the second part, we'll look at the available resources that you can start off with for your own research in planetary science. And so this includes the data source, the software, and the reading material that you would need to begin your career as a planetary scientist, or even if you're an amateur scientist, you can always find these useful, and they are mostly free things that you can use. So yeah, so what is remote sensing? Remote sensing is the art of acquiring information about an object without actually getting in physical contact with it. Now, as an example, the first image that you see over here, this is a telescopic image of planet Mars, and it has been taken through a 6-inch Maksutov Cassegrain telescope, which is not the most powerful telescope that we have on Earth. There are much more powerful telescopes with much bigger apertures, but this is just a hobby telescope that even you can get, and you can get a pretty cool picture of Mars like this from this telescope. And there are details also in this image. For example, the southern highlands you can see as a darker shade, the northern highlands as much smoother, and you can also see the southern polar cap over here. All this from like your backyard you can do it. Second, you have space telescopes. For example, the Hubble Space Telescope, which can give you more detailed views of the planet Mars. In this image, you can see these blue areas. These are actually water, frost, ice clouds that are like they're swirling over the surface of Mars. And also at some places you can see dust storms also. For example, here in the northern area and here near the Hellas Basin. So this sort of details you can get from like Earth-based telescopes and space telescopes. However, the Earth's atmosphere is a big hindrance to telescopic observation of celestial bodies, since it interacts with the incoming electromagnetic energy and severely alters it. So, and also because of the distance between celestial objects is quite large, the resolution is a lot compromised. So that's why you had the Hubble Space Telescope. But even then, this image that you see of Mars taken with the Hubble Space Telescope is from a distance of 68 million kilometers. So it would have been much better if we could get closer to the surface of the planets, and that is the sole purpose of a satellite, which is often referred to as an orbiter, as it orbits the target planetary body. So we often use these words satellite, orbiters interchangeably. So the satellite in this picture that you see is the Mars Reconnaissance Orbiter, a very successful mission that was sent to Mars. It was launched in 2005, and it is still active for over 16 years, and it's still passing on data that you can use to do science, and people are doing remarkable science with it. The image that below that you see is taken from a very small area. You see it's about like 50 meters wide. It's captured by an instrument called the High Resolution Imaging Science Experiment, or HiRISE in short. And it is capable of taking pictures of the Martian surface at breathtaking resolutions of 25 centimeters per pixel, which is phenomenal. And in this image, you can see these layers that you see. These are sedimentary rocks that formed millions to maybe billions of years ago from dust and fine sediments that settled down from the atmosphere and were later cemented. Right at the first glance, what you can see are cyclical variations in the sediment properties that is revealed through the sharp contrast changes. And there's also this bluish material that is occupying the low-lying areas. This is just the dust that has been carried by the wind and deposited in topographic low areas. And this the last column that you see, here you see the Martian rover Opportunity that has acquired this image of the blueberries or the hematite spherules from the Meridiani Planum region. This is taken from a very close distance. You can see the scale is very, very fine. It's 50 millimeters, sorry. However, it's not easy to send a rover to every point on the surface of a planet for obvious reasons. So hence, that's why you need orbital instruments that can map the entire globe, albeit at a coarser resolution, but you can still get a broad idea of how things are on the surface of a planet. And without orbiters, you can never reach to the state where you can land a rover on the surface. So these are very crucial for any sort of serious scientific work that you want to do on some foreign planet. Yeah. So now we come to photogeology, and the first thing that you do with remotely sensed data, or any data in fact, is you look at it. But what exactly do you look at? The things are here are a couple of list of things that you keep in mind when you're studying satellite optical imagery. First, you look at the tone. Tone and texture are the two most important things out of all of them. So the first thing is the tone, which refers to the relative brightness and colors of objects as seen in the images. It could be you can use terms like bright, dark, blue, red, etc. Second is the texture. Texture is the frequency of tonal variations. So that means a very quick and abrupt variation in tone would give you a rough texture. On the other hand, a very uniform tone would give you a smooth texture. yeah, and apart from these, you also take note of the shape, the relative size, the spatial dimensions, and the association of these objects with other objects in the vicinity. A last important thing that we often find very useful in satellite data interpretation are the shadows cast by the individual objects. This is important because often you do not know how tall or how deep a certain feature is. So shadows can give you a very quick idea of those things. You can even go on to doing quantitative measurements using shadows, although it's very difficult and tedious, but you can still do it. And with these in mind, we can start exploring the data sets. So we'll start by looking at some of the full disk images of some planetary bodies of our solar system. The first image we look at is of Io. It's the innermost Galilean satellite that orbits Jupiter, and Io is the most volcanically active body in the solar system. Its surface is covered by over 400 volcanoes, and out of which 150 are always active even as we speak. This image was acquired by the Galileo spacecraft. In this image, you can see two volcanic plumes. One here, which is coming from the Pilian Patera. Patera means a crater in the planetary terminology, and it could be a volcanic crater, it could be an impact related crater, but any circular depression of is called a patera. And here you see the second one, which is called the Prometheus plume. This is about 140 kilometers high, the one from the Pilian Patera, and the one from the Prometheus plume, that is about 75 kilometers high. And the interesting thing is that the Prometheus plume, this one, it was visible in images that were first captured by Voyager 1 flyby in 1979. And it is present in the images that were taken by the Galileo spacecraft 18 years later. So this volcano has been active for a very long time, and it might still be active even today. Apart from these, you also see a lot of coloration on the surface, like these yellow, reddish, and other colors. These colors are they come out from the sulfur and the sulfur dioxide that are spewed out from these volcanoes. And all of this makes Io the reddest object in the solar system. So if some of you are wondering, yes, it is so red that you can see it even in these images. Next, also because of this continuous volcanism, the surface of Io is recycled very fast, and therefore it has the youngest surface of all the bodies in the solar system. Sorry. Next, we take a look at another of the satellites of Jupiter. This time it's Callisto. Sorry. So in Callisto is the fourth and outermost of the Galilean satellites. First of all, what you see in this image is all bright and dark surface, and although it is the darkest of all the Galilean satellites, but it's still twice as bright as our own moon. The pronounced feature over here, this circular feature, it actually extends all the way up to here, is called the Valhalla multi-ring impact basin, and it extends for about 2,000 kilometers from the center, so it's huge. The most striking features on the surface of Callisto are its craters. Callisto is famous for craters, and it is believed that these bright areas that you see, these are made of mostly ice, and the darker areas are highly eroded ice core materials. Also, Callisto gets the title of having the oldest surface of all the bodies in the solar system, and you might want to compare this with Io, which I just told in the previous slide, which had the youngest surface, and Callisto has the oldest surface. Both of them are satellites of Jupiter. Next is Enceladus. This is the brightest object in the solar system, Enceladus. That's because its surface is predominantly covered in ice, and that makes it highly reflective. Almost it reaches 100% reflectivity, and hence that explains its brightness. Although its size is very small, it's 540 kilometers across. The most striking feature that blew the minds of scientists were these active erupting geysers from the near the southern pole. And these geysers, the plumes that they shot out, these jets, they were found to contain materials like grains, ice grains, water vapor, nitrogen, carbon dioxide, ammonia, methane, and other organic compounds. And these geysers are long lived, and they are there for a long time. Since the missions that they have been observed, all of them have found these geysers, and in fact the material that has been ejected from these geysers forms a ring around the planet's the Saturn. So that's called the ring E. And scientists had figured this out after they actually saw these geysers spewing out like the plumes of water laden with all these minerals. And the cause of these geysers is mostly Saturn's extreme tidal forces on Enceladus, which causes heating and cooling of ice pockets or water pockets that lie underneath the surface. Coming next to our neighbor, we have this this is Venus. It's been taken by the Mariner 10 spacecraft, but you don't really get to see the surface because everything is covered in thick clouds. The atmosphere of Venus is so dense that you cannot see its surface in the visible range of the electromagnetic spectrum, and not even in much of the some of the infrared also. So next we come to the surface. We actually get down to the surface. Now so far we were looking at the full disk images of these objects, but now let's look at the surface features. Using the same elements that we discussed for visual interpretations, we can identify features. For example, here you see there are fluvial channels and deltas. This is from Mars, and there are also these lines which are probably eroded away by winds, and maybe later they'll turn into yardans. And here's a picture which shows you several cross-cutting grabens. Grabens are normal faults or horsts, faults bounded on both blocks bounded on either side by normal faults, and they cross-cut. So several ages they are formed over a long period of time, and there are craters also, little craters splattered all across the surface. Here in the center we have Olympus Mons. It is the highest volcanic highest volcano in the entire solar system. It's about 21 kilometers high. It's so high that its top even sticks out of the atmosphere. And this image is unlike these images. This image is an off-Nadir image. That is, it is taken at a slightly slanting angle. So that's why you get a perspective view, and you know how high the thing is high. You get the perspective. On the right, you see these are again grabens, but these are from Mercury, planet Mercury. And lastly, here we have this is a thrust fault that has been displaced by a normal fault. So interesting. And another thing that you might want to keep in mind is, don't always expect that you find the same sort of geomorphological features on these other planetary bodies. Many times you will come across things that you have never seen before, and that will be a challenge for you to explain how these features have formed. And that would be really fun if you ever come across any such features. There are a lot of features already which are unexplained, and people are working on them, so you can take a look at those features. Topography, yeah. So far we were only looking at optical images, but optical images are good for only visual identification and some sort of visual classification. So it's more like qualitative and subjective. However, if you want to carry out more quantitative measurements, you would need information on the elevation of the objects. There's a lot more you could do if you have the elevation values along with the optical values. We call it geo-registration. So if you have both of them registered like the same, you have the same elevation value for the pixel that you are talking about. So you can do a lot of quantitative analysis with that. It's like adding a new dimension to the way you visualize planetary bodies. So two-dimensional things become three-dimensional. On the left, this is an optical color image of Mars taken from the created by images from the Viking orbiter, and this is a global shape model or elevation model or digital elevation model, whatever it refers to, the an image that contains only the elevation values. So this is not taken by a camera or something. This is actually taken by a laser altimeter, and it gives you the values of the surface heights. For example, here you can see it's the scale is mentioned. The 0 is the datum, and anything above it is higher in altitude, and anything in the bluer shades is low in altitude. So these are the volcanoes, they stand up high, and these are the canyons and the low-lying regions of Mars, which are below the surface datum. So what you do is, when you warp this optical image on the elevation image, you get a 3D rendering like this. And that, first of all, it's aesthetically very pleasing and beautiful to look at a thing like this. But more importantly, observe that the volcano over here is Spavnis Mons. It's completely flat. You don't see the elevation. If you have to infer that it is a volcano, it will be only through your experience. But here, after it's 3D rendered, you can see it is elevated, and not just it, the other features also, the Olympus Mons and the other volcanoes, Astreas and Pavonis, Arcia Mons. And in the center also, you have Valles Marineris, which is well depressed the way it is supposed to be, unlike here, where you have to again infer it from your own experience that it is a depression. So you can see that having a topography information makes you very, it enables you to do a lot of things. So much so that after a certain amount of time, if you are not having the topographic information, you will always feel that you are missing out something. Moving on to the next slide. Here I will describe some of the applications of the topographic data. Firstly, if you combine it with the gravity information, you can infer the internal structure of a planet. Here in this example, the molar topography was combined with the gravity data, and both were used to derive a map of the crustal thickness of Mars, which is a very important thing if you want to do some sort of geodynamic studies or on extraterrestrial planets and bodies. Here is a second application. This is from one of my own studies that we did a couple of years back. Here we found some strange circular features, elliptical features in one of the canyons of Valles Marineris called Juvente Chasma, and these were closed elliptical outcrop patterns that had inward dipping layers that resembled structural basins. But I cannot tell that it is a fold, or if it is a fold, or what sort of fold it is, just by looking at the image. So what I had to do was I had to pull out the elevation data, and in that elevation data I used it to derive the dips of these limbs, and I found that they were both dipping inwards. And similarly, I carried out this for many other craters, and we were able to plot the dips of the axial planes and the plunges of the fold axis in these plots, and we were able to make some inferences that were relevant for our study at that time. A few other applications of topography is you can automatically identify stream channels like these. These are automatically identified, these are not manually drawn. So if you give the topographic data to the computer and there are certain algorithms, they can immediately identify stream channels, depressions and sort of things. And from those you can even delineate these catchment areas and watershed analysis and a lot of other hydrology stuff also that you could do once you have the topography data. And this is not the end of it. There are lots and lots of other applications in geodynamics, morphoparametric analysis, numerical modeling, and on the list goes. So we'll move on to the next point, which is how do you get the topography data? Since it is so important, it's also important to know how we acquire the data. First is the laser altimetry. It's very simple. This is the MOLA that I have been talking about. for so long, MOLA instrument. This is a source of laser. So this shoots out laser to the surface of a planet. It's actually upside down in this image. It shoots out laser to the surface of the planet, and the laser reflects back and is collected by this collecting telescope over here. This is how it is in action. So it basically determines the range between the instrument and the laser by measuring the round trip time for the laser pulse. So the advantages are it's very high resolution for global studies and regional studies. Like it gives you kilometer scale resolution, which is pretty good for global studies. Next, it is very accurate. In fact, it is the gold standard. And other TEMs, whenever you create those TEMs yourself, you need to tie them to the MOLA base elevation values. Then only it is considered legitimate for analysis. Third is there is one disadvantage that you cannot do with meter scale analysis. For example, if you are doing in the previous example, where I was studying those folds, that I was not able to do with the MOLA because the resolution was quite coarse for that sort of studies. But there is a way around, and I will come to that in one of the later slides. This you see profile over here is a north to south profile of Mars, and see a couple of interesting things. This point over here marks the boundary between the northern hemisphere and the southern hemisphere. There's a dichotomy. It's not actually the northern hemisphere and the southern hemisphere. It's actually a dichotomy on Mars, that the northern plains of Mars are much flatter, smoother, and the crustal thickness is much less compared to the southern plains. So that's the most important dichotomy that we have on Mars. It's marked by three things: very thin crustal thickness, second, very smooth surface, and also the elevation is much lower for the northern surface as compared to the south. So this is being demonstrated from the MOLA data. How beautifully you can see it. Now, if you remember from the earlier slide, I told you that you cannot see into the surface of Venus and what's going on inside underneath those clouds. But there is actually a way but you have to go to a different wavelength range of the electromagnetic spectrum and use radar data. Using the synthetic aperture radars, you can find the superficial features of planetary surfaces that are covered in clouds and things. And SAR can also give you digital elevation models, just like you had from the laser altimeter. However, the resolution is not always the same. This is a map of the Venus colorized, and it has been converted into the elevation values, and it is obtained from the Magellan SAR, synthetic aperture radar, on board the Magellan spacecraft that orbited Venus. There is also a third way you can find the digital elevation models. You can calculate the digital elevation models, or rather generate them, and that is using stereo photogrammetry. If you have a left and a right image of the same target from satellite taken at two different angles, you can combine them to get a very accurate estimate of the elevation values. However, you need to tie this to one of the global DEMs, for example, the MOLA DEM that I told you, and you can then carry on very fine scale calculations like layer thickness measurements, dips and strikes of layers, stress strain calculations, and lots of other things. So that's all about topography and their importance. Next, we move on to the surface composition. That is also a very important thing that we need to know what the surface is made of, what sort of minerals and chemical elements comprise the surface. So just like to get an idea of the geophysical, geodynamical aspects of planetary surfaces, you needed the topography information, which was an added dimension. So here also you need to add a third dimension, but this time it's in the spectral domain. You have to add this dimension. So reflectance spectroscopy is the most commonly used technique to attain this goal. And light in the ultraviolet, visible, and the infrared, the near infrared, that is used for this purpose. And the basic principle is that every mineral has its own unique way of interacting with electromagnetic energy, and thereby it leaves its characteristic signature in the light that gets reflected off it. This plot you see here is a plot of the reflectance spectra of different minerals like hematite, magnesium bearing olivine, iron bearing olivine, plagioclase, low calcium pyroxene, and high calcium pyroxenes. And you can see that they are all characteristic and distinct in their own ways. But how does this actually work? I'll give you a simple demonstration of how this works. Is simple, think of it like this. Here is the sun, which is a source of light. The light that comes from the sun is incident on the surface of a planetary body. We have the moon for here as an example, and it gets reflected off from the planetary surface after interacting with the materials that were present at that location. Then it is captured by the satellite that is orbiting the planet. And inside the satellite, there are some like instruments, the hyperspectral instruments, where inside of which you have again some arrangement that splits the light into the different colors, the color components, and each color component is imaged as a separate file, and they are all stacked together. After they're all stacked together, as you can see over here, you take the pixel values for every location, one particular location from every of these images, and you simply plot it like this against the wavelengths. This gives you the reflectance spectra of that material that you were looking at, and using the absorption bands, where they occur, how deep they are, you can make some relevant interpretations about the compositional makeup of the surface. There are two ways of doing this. One is called the multispectral, where you have fewer bands and they are far and wide apart. So these are good for like change detection, global and some global studies, because they do not take up a lot of data volume. So the images can be used to map the entire surface of the planets, and these are basically done based on the band ratios and spectral slopes sort of things. The absorption features are not visible in multispectral images, so you will get some sort of like bar plot like thing like this, as you can see over here. On the other hand, if you come to hyperspectral, the number of bands is not just too many, but they are continuous. Unlike here these were not continuous. There were big gaps between these wavelength ranges. That's why it's called multispectral bands. But in hyperspectral, they are assumed to be continuous, so that instead of plots like these, you have a continuous linear plot like that. And in these linear plots, you can look at the specific locations where absorptions are happening and what sort of absorption it is, how deep it is. You can still do all the things that you were doing with the multispectral, but here you can do it with more rigor. You can also do some advanced things like spectral unmixing, radiative transfer modeling, and quantitative estimation of mineral abundances, along with the point that you can also identify individual mineral species using hyperspectral, which you are not able to do with multispectral. You can only get an idea of what elements are there, like a broad vague idea, but exact elements, if you want to know, exact minerals, if you want to know, you'll have to come over to hyperspectral. An example is here you have for the multispectral, you have the Clementine iron map of the moon, and you see that there are these patches which show you the concentrations of iron, but this is a global study and it's quite coarse. However, if you come to hyperspectral, you will see that it's not covering the entire planet. It's only present at a few points all over the surface. But what you can see is that there are different minerals that are identified over here. For example, phyllosilicates, silica, chlorides, carbonates, sulfates, all these you can identify using hyperspectral images, but not with multispectral. Multispectral will only give you the, for example, the iron abundances, as shown over here. There are a lot of minerals that you can identify through hyperspectral remote sensing. Igneous minerals like olivines, pyroxenes, and different types of ice like water ice, carbon dioxide ice. Apart from this, a lot of aqueous minerals are also identified like sulfates, phyllosilicates, carbonates, hydrated silicates, and even organic compounds are also detectable using hyperspectral imagery. Here's an example of how this works. First, you decide where you want to carry out the analysis of hyperspectral, and then from the spectral library, your job is to compare the spectra of these elements and see what matches with them. That is a very difficult thing to do if you had millions and millions of pixels. So what you do is you devise some smart way of doing it automatically. One of those ways is called summary products, where you create some formula that captures the band positions and the depths of the bands, and you just run those algorithms on the images, and you get maps like these, which shows you the element, the mineral distribution of that location. For example, this shows you the yellow thing is kaiserite, and the blue thing is somolnokite, most likely. And we had also repeated this work, but we had updated the summary parameters, and we got a much finer like resolution of the mineral distributions. And interestingly, you can again bring back the DEM that we discussed earlier, and you can use these DEMs to do a 3D rendering of the mineral distribution, and then you get wonderful like scientific insights about the distribution of minerals. For example, you see that the red material is only present at the higher elevation, and it's not there, it's dominated by the other mineral in the lower elevations. Apart from this, there are other modes of orbital remote sensing, such as thermal remote sensing, where you measure the emissivity of a surface in contrast to the reflectance, which was like used in the hyperspectral reflectance spectroscopy. You get the thermal inertia, which will give you the grain sizes and degree of induration of the materials. You also have UV, X-ray, gamma ray, neutron spectroscopy, which you can use to study the atmosphere and even get ideas about the elemental composition. These are often relying on the high energy particles that come from the solar wind or the cosmic radiations. And you also have radar, with which you can ground penetrating radar, with which you can study buried bodies of ice, glaciers, and biosphere and such things.
Hello.
Hello.
Could you please
Hello.
could you please finish your talk?
Yeah. I'll be finishing off in 5 minutes. Yeah. So some resources to get you started are like I will discuss some of the data sets, the software, and the reading materials that you might find useful. First of all, you have it in your computer already, I guess. Google Earth. If you check Google Earth, there are a few like options on top, and on one of them takes you to the to Mars and Moon. So if you for example click on Mars, you will get something like this. And on the left side, if you check, there'll be something called a spacecraft imagery, which you can use to check out whatever like images are available. For example, here I have clicked on the prism images for the locations on Valles Marineris, and you can download the images. You can even like check the CTX high rise, and that will be very fun and cool thing to try out. So that's one thing. Second, if you want to download the data for scientific work, you can always go to the Planetary data system. You can search based on the target or the mission that you are interested in. Next, if you're interested only in the inner solar system bodies like Mars, Mercury, Moon, and Venus, you can check out the Orbital Data Explorer. There are 4 Mars Orbital Data Explorer is displayed over here. It's again on the PDS Geosciences node, and you can easily figure your way like out how to get the data and start downloading. This all is free and easily available. A third good option is JMars, because most of us don't have ArcGIS. ArcGIS is very expensive. JMars is capable of doing a lot of things. It has all the data sets available for you, and you can even do elevation profiling, create shape files, and many other things that you can check out. It's also free. A good alternative to ArcGIS would be QGIS. Because ArcGIS is very free, very expensive. QGIS you can download, and you can start analyzing your data that you will download if you download from the Orbital Data Explorer or the PDS using QGIS. It's pretty straightforward, and there are lots and lots of tutorials online which you can also use. Then there is USGS ISIS, which is the integrated software for imagers and spectrometers. This is like host of computer programs that you can do to like a lot of things, from spectroscopic analysis to map projections to corrections, and the list is very long. You might check out, but trying this out is at first it might be a little difficult for those who are not well acquainted with the Unix environment, because it only runs on Linux. But it's still worth giving a try, and it's very fun. And you can even generate DEMs if you integrate this with the AIM stereo pipeline, and that would be also a nice exercise. But You can try it out later. Some of the software also include coding languages such as Python and MATLAB, because you often have to code things. Python would be the better choice because it's free, although MATLAB is also equally good. And there are a lot of things that it will enable you to do once you have these two. For example, data visualization, spectral analysis, and you can read the list. There's lots and lots of things. Some super cool things like modeling and simulations are also possible using these software, and it's all free. If you are interested in research papers, you can always go to the astrophysics data system, which is available, but I'm not sure you will always find the papers because papers are not always free. But you can reach out to your friends or any one of us, and we'll help you out if it is available with us. And lastly, here are some of the books that you could start reading if you want, and this will give you some more ideas on which direction you want to proceed. And these are just my favorite books, although there's lots and lots of more books and review papers that you must read if you are interested in this field. And yeah, that's where I would like to leave you for today, and I hope to see some of you in this field in the future, and let me know if there's something I can help you or any of us, the three of us, can help you with. We'll be always glad to engage with you. Thank you.
Thank you, Raman, for the excellent talk. And we have a quick questions.
Yeah. Dr. Mishra asked that scientists have already detected water resources on Mars. Can this data, along with other favorable conditions, lead to the habitation of human race on this planet? So, Priyaprada, I would like to answer this question.
Yeah, sure.
Yes, people are thinking about colonizing. I will rather use the term colonizing Mars and Moon. This process, they are thinking it from 1970s. This is not new. And the recent mission, on which I will be giving my talk, that the Perseverance mission, one of the major objective of the mission is to prepare for human exploration. Okay, prepare for future human exploration. It carries certain instrument and some technology demonstration programs that will help us to prepare for future manned mission and driving manned vehicles, and also for future astronauts to thrive there. So I will try to cover this thing and touch upon these things in my presentation as well. So for now, I could, he has asked another question as well, that can the different geological data be applied to the evolution of Earth as well? Ranjanda?
Hello, Shom. Can you please restate that question once again?
Yeah, he asked that can the different geological data
of
apply
Mars,
to the
geological data?
Yes, sir. Okay. So, Ranjanda, the question is, can this geological data of Mars be applied for the evolution of Earth?
Yeah, definitely. Because on Earth, first of all, one of the most important things is on Earth you do not have you cannot study every part of the Earth. First of all, it's vegetation covered, and a lot of recycling happens because of active tectonism on Earth. However, Mars is tectonically dead for long. So many of the features that had operated way back in the geological past, they are still preserved, and they can be used as analogs to study things happening on Earth. So yes, that is very important. And secondly, also, since similar processes like winds are operating on Mars, and there is no urbanization and vegetations on the planet, so you can see them in full action. So that's also one other thing that you can study, the geomorphic processes in much more detail.
Especially the Archean part, the Indian part. The Indian region for Earth to enter Indian part is lost during the moon formation. However, we have to enter some preserve on Mars. So if you analyze this the Martian period material of Mars, so somehow we can tell something about what happened on Earth, what was there on Earth, Korean people, earlier Archean people. So in that sense, it is very interesting to study the Martian center. And I'd like to add one that water questions that you asked Dr. Mishra. See, the liquid water on the surface of Mars is actually, the pure state of liquid water is actually thermodynamically unstable. So, getting close to the liquid water on Mars right now is difficult. However, we have evidence of impure phase of liquid water, a very good evidence, okay, in Phoenix Lambda, that is the only one. However, we have liquid salty water in subsurface level. So if you can acquire those the surface water, like the workers from Sierra Lambda was also last few years that they have identified a layer of water within the surface. Like that, if you can detect the horizon or the area where this liquid water is there, so this radar data, our remote sensing data, then we can use those resources for human settlement there if needed.
Okay, I think we don't have. One more question. Kaustubh Chatterjee has asked that in the outer region, what is the proportion of carbon dioxide ice and water ice? And second one, how reverse fault can be identified from satellite images?
Okay, so I'm assuming that Kaustubh is referring to the outer part of the solar system. So yeah, the proportion
I think he is mentioning about Mars. I think. Yeah, I think Kaustubh can unmute and ask directly.
Thank you.
It should be better.
Thank you. There are only two questions. What is in the outer solar region, in the outer solar system, what is an estimated proportion of CO2 ice and H2O ice? And the second is for the Mars image. The fault or lineament can be understood, but how one can assert that that's a reverse fault? Does we use the gravity radar?
Right. So in the outer solar system, after you go beyond the first line, where water starts freezing and it starts condensing into ice, you first meet these two of the gas giants, Jupiter and Saturn. So they are mostly hydrogen and helium. But if you go beyond them, you meet the icy giants, which are Uranus and Neptune. So so it goes on increasing because of the temperature. And if you go even further beyond the Kuiper belt, you find lots and lots of water ice. However, if you compare the Kuiper belt objects with the asteroids are mostly silicates and chondrite material. So further you go beyond, the proportion of water ice keeps on increasing. And secondly, how reverse faults can be identified from satellite images. Reverse faults in planetary context are often referred to as wrinkle ridges. And that's because they have a very wrinkled appearance. That is the first sign that you might look for, like identifying a reverse fault. Apart from that, whenever you see a linear feature and you're not sure if it is a reverse or a normal fault, you can simply turn to the DEM, and the DEM will, in many ways, it can tell you whether it's a normal fault or a reverse fault. But mostly on Mars and Moon, reverse faults are seen to have a very wrinkled surface, and that's how we call it. It's a reverse fault.
Thank you. Thank you for your answer.
Another question we have here, Nilabho Sheth, he asked that is Mars is technologically active and why?
I think
Inactive actually, I think.
the question was
I think I am sorry. He asked that is Mars is technically inactive and why?
Most of the reason why some planet goes from tectonically active to inactive is when it starts losing heat, and also when it starts losing water for some reason. So these both are very important. For Mars, we have a lot of water, so that's not a problem. But because of its smaller size, it has lost a lot of its heat, and that is what led to also the loss of its magnetic field. And because of the loss of the magnetic field, Mars also lost the atmosphere, which was stripped away by the solar wind. So all of it is actually related to the amount of heat a body can retain. You remember one of the earlier slides I showed you, Callisto. So a similar thing has also happened with Callisto. The reason it has the oldest surface in the solar system is because it is so far away from Jupiter that it does not have tidal stresses on it that can generate heat. Neither is it big enough and doesn't have enough radionuclides that can produce internal heat. And also it's very far away from the sun. So all of this has led to the tectonical end of planets like these, which fall at a smaller size.
Okay, thanks for explanation, Ranjan. So
We have one more question. We have one more question.
You can answer it right now, or you can answer after you talk.
No, I think we can cover it, and then I would start my presentation. Dr. Mishra,
Just cover it and we will start.
Dr. Mishra, can you please read out your question? I couldn't follow right properly.
No, whether orbital remote sensing or land rover data of Mars will be more accurate. Which data will be more accurate? Whether land rover data or orbital remote sensing data?
In science perspective, you can use both, and both are to some extent are accurate. Okay, so scientists are using as they after various processing of the raw data and calibration of data, and then the science ready data has finally produced. So these data are accurate, you can use, but the problem will be about the extent, the spatial extent. For remote for orbiter data, the extent of the data per pixel or the scene will be covered a huge area, and you will get a crude data in comparison to the rover one. But for the drawback perspective from a rover data is it can traverse up to a few kilometers. Okay, you cannot generate a map, or you cannot study a global area or the regional basis.
Regional area.
Yeah. So I think I should start my presentation right on.
Yes.
Yeah. With all of your permission, I am just sharing my screen.
Okay.
Yeah. Yeah. Is this visible?
Yeah, perfect. Go on.
Yeah. Thank you. Thank you, everyone. Very good afternoon to you. Dr. Nivedita Chakraborty and Mrs. Indani Mondal has already introduced us, all of us. But let me say a few words about myself. I'm Shubham Sarkar. Completed my BSc and MSc from Presidency University, Kolkata, and then secured the DST Inspire Fellowship and joined the Space Application Center. It's a institute of in ISRO. So under the guidance of Mr. Shvetadru Bhattacharya, he is present here, and he is a student of Durgapur Government College and taught by Dr. Maji and Dr. Mahapatra. And now I am about to submit my PhD thesis on spectroscopic and geochemical characterization of Martian analog minerals from different parts of Indian subcontinents. Although my main focus of research is to study the hot springs related mineralogy and their astrobiological implications, this work will also help in future sensor development and to find these minerals on the different planetary bodies. So you can think that I use two words that may be hard to follow for some of you, like astrobiology and sensor development. Just be patient. At the end of this presentation, I think you will get to know what these words mean. So mainly today I will be talking about the recent rover mission by NASA, which is still currently working on the surface of Mars. That is the Perseverance rover. And as this talk is mainly intended for targeted to the BSc students, I have tried to be as lucid as possible and to engage the young minds to the subject of planetary science. So let us start. So here is mainly the recent Mars missions by NASA. In the upper part, you could see the orbiter missions. Already, Rajanda has told the difference between the orbiter and the rover missions and the lander missions. So here is the Mars Odyssey, Mars Reconnaissance Orbiter, the MAVEN orbiter, the ESA's Trace Gas Orbiter, and also the rover instruments like Opportunity, Curiosity, the Insight Lander, and the Perseverance, the main focus of this talk. And the ESA ExoMars rover, it is destined to go in future. But just focus on the lower portion. Okay. So here, it's the evolving Mars science themes over the years. It's not like that these themes are generated in this time frame, but all these missions, they try to follow this Mars science theme. So why to send this? Okay, these missions. Like first, the Mars science theme was to follow the water on Mars. Then people are sanguine about the water availability on Mars using the opportunity data and the curiosity rover data. Then they started exploring the habitability perspective. Was Mars habitable on the past, or it is habitable till now? So for that, the Curiosity started working on that basis, and Perseverance is carrying forward this work too. And when the habitability perspective is achieved, then people try to seek signatures of life. So naturally, we could see the seeking biosignatures preservation potential for the different parts of Mars. So mainly, Perseverance is working on to explore the habitability perspective and seeking signs of life on Mars. So all these missions, there are hidden objective in all of this is to prepare for human explorations on the red planet. So coming to the next point, so why to send rovers? Why to invest in rover missions? As Mars science can be achieved using telescopic and orbiter-based instruments. So already Dr. Sarkar has already discussed about the basic limitations of orbiter-based platforms. First of all, it can cover the whole surface of the planet, but the spatial extent is too coarse. Okay, for example, the average resolution of a multispectral instrument is 20 to 30 meters. That means each pixel of a satellite image from that sensor is of 20 to 30 meter in length and width. So the data from a 30 meter pixel, a 30 meter grid is represented in one pixel of your computer. So for global map production, this is quite handy, no doubt about it. But as a geologist, we not only need to see some old and crude map prepared by the previous workers, but yes, they can help us to understand the general association of lithology and the structural aspects of the area of interest. But to start with, you need to carry out a field work. Okay, you have to go to the field, measure the structural orientations, understand the basic lithology, and finally collect the samples for further studies in lab. So the Perseverance rover will do all of this for us. So we cannot go there as of now. So we sent the robot geologist on Mars. Fine, we sent the rover, but where it will land? So as we can cover a maximum of few kilometers with a rover, so landing sites will must be precisely determined. In this image, you can see the past landing sites of Martian rovers. So this is basically a topography map. Already Priyabrata and Ranjana both have shown and referred to this map. So I just mentioned a few points. Thus, these blue areas are the lowlands and the red areas are the highlands. And here, the highest point of the Mars, the highest point of the entire solar system, that is the Olympus Mons. Okay, so it's coming up, giving you the red, and it's even the white color. Okay, because of its height, it's more than 20 kilometers of high from the Martian datum. So you could see a distinct difference between the northern lowland and the southern highland. But in case of Earth, we could find all the continental landmass is towards the northern hemisphere, and in some southern hemisphere, mostly this is covered by ocean. But so the general depression is from north to south in case of Earth. For Mars, it is quite reverse. So this area, the greenish area here, is called the Martian dichotomy. Okay, it is a juncture between the southern highland and the northern lowland. And except for two landing missions by NASA, that Phoenix and Viking, all the other missions are targeted in these areas only. Okay. So I am restricted this presentation mainly to the past and present rover and orbiter sent to by NASA people. But apart from that, ISRO has achieved a tremendous goal that it sent a orbiter mission on their first chance, the mission on Mars, the Mangalyaan mission. But here I wanted to show you the ongoing Mars science perspective view. So I took these missions. They are actually linked to one another. Okay. So coming to the point, so why to choose this dichotomy boundary? Because this area, as they show the latitudinal differences, they can show you some. They can provide you with rocks from the highland as well that are carried by any agent to the lowland, and also the the original rocks of the lowland areas. And it can also give you the window to search the different sedimentary layers. As shown in his presentation, the sedimentary strata, we can study them to understand the past geological activities there. Okay, so after that, okay, fine. We have targeted this dichotomy boundary, and for perseverance, we have targeted a crater called the Jezero crater. So this is Jezero crater, and here in the left, the rover is destined to land on the left side, as you could see in this interactive video here. So yeah, it landed on the left portion. The ellipse you are seeing here, the circle, is the term the landing ellipse. The rover is destined to land the center of this mark, and it may land anywhere within the elliptical area due to some technical issues, but the white line is anticipated trajectory, and the blue line here is the river flowing from the left side, the western side, and deposited the sediments in the form of delta. Okay, so the crater was once a basaltic surface, then the impact happened and the crater formed, and then on the crater, the river from left deposited some sediments, and this lake and formed this delta. So here in the false color composite image, you could see the mineralogical variations of Jezero crater. So the yellowish and greenish area are comprised of olivine and carbonate rocks, and the sedimentary layers of the delta region is greenish to purple in color. And the older crater floor unit, that is comprised of the altered basaltic layers, that is mainly the smectite rich clays and phyllosilicate minerals. They are pretty much brownish in color in this map. Okay. So, okay, let us see how the rover had landed. So the procedure of the landing was based on three distinct. First, that the detachment of the parachute, deployment of the parachute, and then he will be seeing the detachment of the heat shield itself below the rover, and after that, deployment of the sky screen thruster. that help the rover for targeted smooth landing. You can see the rover at the lower left corner of this video, and suspended with the help of three cables from the thruster. And the upper left video is shot from directly from the rover in upward direction. Okay, and after the rover successfully touched down, the suspension cable detached and the thruster flew away and crash landed on somewhere on Martian surface. So I just kept this video in this presentation to give you a glimpse of the power of humanity. This is not any CGI generated image or any scene taken from Marvel movies. This is something people have done on an alien planet. Okay. So fine. So it has landed successfully on the surface of Mars. But why? For what purpose? So much time, so much money has been invested. What the rover will do? Here are the basic objectives of the rover that is ought to be fulfilled during its working tenure, achieving which the mission will be declared as success. So, like the first two objectives are geology and astrobiology, like to study the rocks and landscape at the landing site to reveal the region's history. And secondly, to determine whether an area of interest was suitable for life, and to look for signature of ancient life history. Okay. And the third and most important objective of this mission is to sample catching. For the first time from Martian surface, people are trying to dig a core and collect core samples, and that will be returned to Earth in successive missions. Okay, by the first half of 2030, it is planned that this mission will make these samples will be returned to Earth for further analysis. And last but not the least, the mission has a hidden objective, as I already said, that prepare for human missions to test certain technologies that will help sustain human presence on Mars and someday in future. Okay. So, how to achieve these goals? How to this Perseverance rover will fulfill its objective? Here are the main instruments of the rover that carries with it, and some of it for the achieving the geology and astrobiological perspective, like this pixel instrument. Okay, that is on the robotic arm. So this pixel instrument is nothing but a X-ray fluorescence. You all heard about XRF. This is a field-based XRF machine. And this Sherlock instrument. The Sherlock, and with it carries with it a camera called Watson. So this Sherlock is a Raman spectrometer. And there is a instrument to analyze the Martian weather that is called MEDA. And the most important of it, our focus of interest right now is the SuperCam. So it is amalgamation of 6 to 7 instruments. It has basically two hyperspectral sensors. One will be capturing data from the visible region of the electromagnetic spectrum, and another will be for the IR domain. So 1.3 micrometer to 2.6 micrometer. And it has a laser-induced background spectra, the LIBS spectrometer, and it also carries a Raman of its own, and along with thermal luminescence spectrometer, and it carries a microphone to capture the Martian sounds. Okay. And another interesting instrument is the RIMFAX, this ground penetrating radar. It will give a glimpse of the subsurface of Mars. And it has a total number of 23 cameras. 23 cameras, believe it or not, 23 cameras, 2 of which are clubbed and called the Mastcam Z. So in American pronunciation, Z is pronounced as Z, so I'm referring is the Mastcam Z. So these two here, one here and one here, these are the left and right Mastcam Z cameras. The stunning imageries you see, I will be showing you some of them. So they are mainly captured by the Mastcam Z. Okay, so with this scientific instrument, they will this rover will pursue its geological and astrobiological objectives, but for human exploration. What it will do? So it carries an instrument called MOXIE. It can produce oxygen from Martian carbon dioxide. So we all know that Martian atmosphere is mainly made up of carbon dioxide. So it's purely, I could say, that purely made up of carbon dioxide. So if further human exploration are planned in future, so it will be quite impossible to carry such a load of oxygen to sustenance of human explorers there. So we have to make oxygen from the atmospheric carbon dioxide. So the MOXIE will do that and try to achieve sustainable amount of oxygen production before human exploration could be think of. So next, another aspect of this mission is the Ingenuity helicopter. Here you are seeing the footage of the first flight of Ingenuity. Okay, so human has successfully flown an aircraft over a different planet after more than 100 years of first flight by Wright brothers. And for to give homage to Wright brothers, the helicopter, this Ingenuity helicopter, carries a piece of cloth from the first aeroplane winged by them. Okay, and it's a good thing to mention that the chief engineer of this Mars helicopter project is of Indian origin. His name is Mr. Bob Balaram, alumni of IIT Madras. So next, the sample catching procedure. Okay. So one of the main objective of Perseverance rover is to collect sample for future return. In this animated video, you could see the step-by-step processes of sample collection by the rover's robotic arm. Here the drill core has been captured and then it will be transferred to the sealing compartment. Okay. Yes, it is transferring to the sealing compartment. Right now, it's going to, yeah. So the sample core has been sealed and it will be stored in the sample cache unit. And these samples will be kept on Mars. Before 2030, these samples will be returned with the help of 2 subsequent missions. Okay. So as of now, total number of 8 core samples of 1.3 centimeter diameter and 6 centimeter in length have been collected. So all of you are following the mission from very beginning, like us. So we were pretty excited about the sample catching procedure. But it will be because it will be the first time the Martian rocks can be analyzed here on Earth. Okay. Although there are some meteorites that are thought to be coming from Mars, but it will be first time the samples, the physical samples that will be coming from Mars. But to the surprise of everyone, the first sample collection operation has failed. No sample could be recovered by the first drilling process. It was made to the headlines of the scientific news portals. People were everywhere was talking about it. Everybody was startled by the non-recovery of the first sample core collected by Perseverance. So here in the left image, you could see the remote micro-imager photograph that is hosted on the SuperCam. It's nothing but a zoomable lens, the zoom lens. It can close. It has a very close range view. It's I could say is a macro lens. Okay, macro camera. So this remote micro-imager image. So you could see a portion of the drill core at the bottom of the drill hole here. Okay, and on the right is the Mastcam Z image, where you could definitely identify the drill cone that is generated by the drilling process itself. Okay, so what happened to the first sample that was tried by Perseverance to collect? So we dug up and we dug up and came up with this. Me and one of my senior Narayan Bose from IIT Kharagpur, we worked at it, and we got time to time input and mentorship from Satadru Bhattacharya, as I already mentioned his name, and Dr. Subhash Pandari, my guide of my PhD thesis. So they helped me a lot. They helped us, me and Narayan, a lot on this. And what did we do? Okay, we started analyzing the SuperCam and LIVS data and came up with these results. What are these? So in the left panel, So you can see some remote microimager photographs near to the first drilling site. Okay, there merely all these images are taken merely a meter to a few meters apart from each other, circling this drill hole. So here in the red circles are the IR spectral points, and the green crosshairs that show here is the laser induced breakdown spectrometer data collection points. So in the middle portion, this is the IR spectra from these points, these 6 points. Okay.
Just one second. Just 1 second. Niganko, can you mute your like? Hello.
Please mute your microphone. Niganko, I think. Please mute your microphone.
Okay. So in the middle, the IR spectra. In this panel at the bottom, this is the USGS spectral library of the minerals, and above are the spectra from Mars surface itself. And we matched them to and came up with that these minerals, these rocks here are nothing but snake-type minerals. Okay, these are aluminium-rich clay minerals and somewhat iron and magnesium-rich, and these data fits well with the laser-induced breakdown spectrometer data, the LIBS peaks. And this is a quite handy instrument that can give the elemental abundance of any surface with the help of a laser beam. Okay, and so we are getting a gross idea about the mineralogy with the help of this IR spectrometer, and we can pinpoint the mineralogy by this LIBS data. So no big deal there. Okay. So in the previous slide, I have already shown you that what we have done. The whole work was done without taking any help from the rover instrument team. As outsider, we are able to do that. So because the data and all other related information like how to process and use the data is freely available. Okay. You just need to have just a little prior knowledge of the subject and to knowledge about the data manipulation and data visualization procedure. So in the next few slides, I will be showing you where to get this information about different instruments and about the data downloading and visualization processes. Though Ranjanda has covered it up in a little, but I will just go a further detail in respect to the Perseverance rover, so that you could work on the rover data on your own. Okay. So here, just you have to go to the site, the pdsgeosciences.wustl.edu. So next, if you click this link, it will be redirected to the PDS Geosciences node. So first of all, you get some information about the data and the recent data that will be published in future. Okay, and here you can get many other links to download not only Mars, from Venus, Mercury, Moon, Earth data as well. So if you click Mars, then the historical Martian data all are freely available here. So starting from the Mariner data, okay, then Viking, lander, orbiter, the Mars Pathfinder rover, and like this Curiosity data also. So let us click the Perseverance rover here. So here the main page of the Perseverance rover's data in PDS. In this left panel that is highlighted in green, these are the basics of the highlights of the instrument itself. Let us see that what the SuperCam holds for us. So here you can find the design and the location of the SuperCam on the instrument itself. So if you scroll down, you could get the basic information about the mass, power, volume of the instrument, and then you get to see the picture and of this man, the Roger Wills. So he is basically the principal investigator of this SuperCam instrument. So for any data and science related question, you can easily ask him and any of his team members, they will help you, I think. So not only supercam like this, you can also click to different and browse to different instruments to get the basic idea about the instrument. Okay, so let us get back to the data portion. So in this area, the highlighted in blue, here is the mainly the data in the under the head of PDS bundles, the data from different instruments you could get here. So let us enter the supercam bundle. So here you would see the introduction to the supercam archive bundle, that is a text file that will just to for that readme text to start with it, with the data processing and all the processes. And for different instrument you will get the calibrated data and the derived data. Okay, so this calibrated data, these are science ready, and the derived data, these are the data where the preliminary science objectives has been fulfilled on the data, and then they are releasing it. Okay, so if to start from scratch, you can use the calibrated data, and you also can use the derived data product also. But this raw data, you can see this raw data portion. So raw data needs some calibration and validation, and all of this information can be found on this bundle. Okay, so there is a volume, a huge PDF file called the Supercam user guide. So where you will get every information that you need there. And another interesting thing, if you scroll down under the tools menu, you could find a March 2020 analyst notebook. Okay, so let us click here. First of all, it will ask for your email address and password. So you could always bypass it by clicking the anonymous link and continue without signing in, and then you will get to see this window. So here not only perseverance, you could visualize and work on and download data from Apollo missions as well. The Apollo, the L-Cross mission from Moon, the Phoenix lander, the Spirit, Opportunity lander, the Curiosity rover, Insight lander, and also the Perseverance rover's data. Okay, so what's next? The basic idea about the mission can be viewed here also. Then in this tab, you could get the interactive map where Perseverance is right now. So these number, like 127, 129, 131, these are the Martian day. Okay, so when Perseverance started its journey, it will be marked as 1, and then within time to time it will be get highlighted and get increasing. So we term the Martian day as sol. Okay, 1 day is 1 sol. So for Mars, I will be referring to sol now on. So if you scroll up and down with your mouse, you can hover with this map, interactive map, and get to see where the rover is as of right now, and if you are getting the data from exactly which point the data is coming. So let us see the data from different sols. You could click here and directly type the number of the sol in this button. But okay, so you are getting the sol number 299 at last. So the data as of now, the sol up to 299 sol, the first 299 days of data has been public. And then you could browse that data and browse different sols. So let us just see a random date like 157. Okay, so here is the first is the overview update. Like here in the highlighted with yellow, what it did, it drove, then some rimfax data was collected, some helicopter data transferred to the rover, and for transferring to Earth itself, because the helicopter for the size and weight purpose, they were restricted their weight to have to restrict the weight of the helicopter to 1.8 kilograms, and so there is no data transfer procedure or hardware can be kept there. So the data to be relayed to the rover itself, and the rover then transfers it to Earth. Okay, then the most important thing what it did is the targeted remote sensing. Okay, so under the targeted remote sensing, these are the data from data number of data from different instruments. The SC is the supercam, but I was mentioned earlier. So from supercam, a total number of 77 data have been generated. And then this MZ is the Mastcam Z. So total number of 220 images has been captured from Mastcam Z. So we cannot call anyone in a selfie freak. One of our we all have some friends like who used to capture image and to upload to Instagram, but perseverance is not less than that. So it can capture a staggering number of 220 images a day. Okay, so okay, jokes apart, but this under this document tab, this upload link and the download link, these are the two very crucial thing for any rover, and not only rover, any planetary and any mission to thrive. Okay, like if you have gone to field, your teacher has briefed at the very beginning of a field work, every morning, that what we will do, and this we will traverse through this countryside and come across these dogs, and then we will collect some data here and there, and then we will collect these samples. And after that, after the day's work, you will have to submit a resume. So first, the thing what the teacher has told you at the very morning of a field work is the uplink, and then you are submitting the resume. This is the downlink. Okay, fine. So at every data collection or operational procedure, people just upload certain things that to the rover handling procedure, that you have to do such works, and then after all the work has been completed, it will generate a report and relay to Earth itself. Okay, let us just jump to the data products. So here you could see the data products, and you could easily identify the instrument behind it, that this ME is the MEDA, and the SC is the supercam, and MZ stands for Mastcam Z. All the informations are available. So let us see an image from Mastcam Z. So let us click here, and it will be like this. So this is the calibration target of the Mastcam camera. Okay, so you have to calibrate the data, the instrument each time you are collecting any data. Like, I just give you a small example about the calibration process. So you see this colored dots here. These are solid colors, and the RGB profile of these colors are known to us. Okay, so when a data is captured, then the people try to match the RGB profile of these areas with the known values, with their known values. So that's how the whole image can be color corrected. So like, this is a raw version of an image. So this is not properly color corrected. So you are getting a grainy and black and white look of a Mastcam Z image. But after the calibration is done, you will get a stunning, beautiful photograph, a colored photograph of Martian outcrop from this image too. So next, let us move to some navcam data. That is the navigation camera. Okay, so it can also give you idea about the association of general geology. So this navcam and the pancam, not pancam, but the mastcam, both can capture stunning panchromatic, stunning panoramic images, which Priyobrodha has already showed us one from Curiosity rover. So these navcam image. Oh, sorry, this is from Perseverance, no? Okay. Yeah, sorry. Okay, I'll finish. So next, the data download process. Always you can here in the quick download button, you can download the data from here, and not only that, this is the main data product file, and that label file, the header, the information about the data, and the quick look JPEG and PNG images to visualize. These are not the science ready files. The science ready file we will get from this data product file here. Okay, so these are the IR spectroscopic data here, but unfortunately, as this is not a conventional camera, this is the spectrometer kind of thing. So no thumbnail can be generated as of now right here. Like this, previously we are seeing the IR spectroscopic data. Next, the visible data is here. You can always jump to it and click, and just these data are just one click away from you. So to end my presentation, let us watch a video of Martian eclipse captured by the Perseverance rover itself using the Mastcam Z camera. It is one of the moon of Mars, that is Phobos, passing the sun. So that's all, everyone. Thanks for your patience. And for any help needed regarding data visualization and interpretation and any other thing, feel free to contact me through my email. I will try to answer your queries to the best of my knowledge. Thank you. Hello.
Thank you very much, Shubham, for the beautiful presentation. I just have a question. Any of you can answer it. I'm asking just as a layman, okay? So forgive me if it seems silly. Would you mind to explain regarding the presence of water in Mars in the past and why it is actually now at present the atmosphere of Mars is thin, I think. So the pressure condition is not permissible for the stable liquid water. So my question is, what may be the reason behind this change of the atmosphere? You are saying, or scientists are saying, that water was present, image of deltas are coming, but at present the atmosphere is not stable and thermodynamically it is not actually possible. So what would be the possible reason for this transition or this kind of?
Yobrada, I think you are the best person to answer this. You are muted. Priyoda, just unmute.
Actually, you are asking the question. Right now, the present is after some months. The clear place of liquid water actually unstable. But there is a possibility the impure phase of liquid water, for example, drying, that is there on the present surface. However, this is.
Priyoda, you are not clearly audible. You are not clearly audible.
Hello.
Much better now. Much better now.
So the pure phase of liquid water actually thermodynamically unstable on the present surface of Mars. However, the impure phase of water, like for say brine and all this stuff, but it is still now not detected. But we have some evidences of droplets of water on the Phoenix rover, the Gander lakes. Okay. Your question is that, yeah, obviously, that water was there on Mars in ancient time. Was actually flooded. Mars was flooded with water. We have beautiful evidences of body network and channel fields and how it has actually disappeared, how all this thing gone. But I think Ranjan has already given the answer before, because that Mars actually lost its internal dynamic. And with its loss of the dynamo, this gravity negative field, all these things, the authority to this atmosphere actually. The gases are removed from the atmosphere. Okay. And what we are getting right now, say in atmosphere, 1 milliwatt pressure. From this 1 milliwatt pressure, we cannot expect liquid water to the surface. So I think the thing actually happened internal, and the cool mountain mass. And how it was happened like this, we do not have any answer. And the government can do something about it. Can you add something of this? Hello?
Okay, thank you.
Hello?
Yes.
Hello. Hello.
Yeah, Shatadruda is here.
Yeah, Shubham, I don't have any questions for you, but I would like to take this opportunity to, if I may allow to do so, to talk to my sir, Dr. Ashish Baji and Dr. Samiran Mahapatra for a minute.
Hello, how are you?
Hello, sir.
Thank you, Shatadru.
How are you, sir?
Fine. How are you?
We are all
Fine,
fine.
sir.
Awesome. Today, after a long time, we could meet you virtually.
Yes, sir. Actually, I am on my way to Sabarmati railway station. I have to catch a train. But since Shubham told me that it will be hosted by this institute, and I immediately told him that assessor will be there, and it is great to see that the Sangal is also joined. Okay. Thank you so much, sir.
Okay.
Thank you.
Thank you, Shatadruda, for joining
And
us.
Nivedita, for your questions, I would like to add a few things what already Priyadata
Yeah,
told.
of course.
In fact, what Ranjan told is that the primary reason behind the using of atmosphere is the size of the mass itself, because that drives that it got quickly the outer core, the liquid core, got solidified quite quickly as compared to that of Earth, which gives rise to the almost the occupation of the magnetosphere, which once upon a time existed at the very early phase. Okay, and therefore the Martian atmosphere was in constant touch with the cosmic rays and solar flares. And because of this high energy particle interactions, there are very speedy dissociations of the atmospheric molecules, CO2 transforming into CO, and then it's losing further the oxygen, and this is the process which is continuously happening, and it is even speeding up the day by day. Now, another interesting aspect is that we always face this kind of questions that a country like India or some other countries for that matter, why you should take care of planetary sciences, okay, or why should we invest so much of money behind understanding what has happened to Mars or maybe Venus. And the simple reason of doing this is that we would like to understand, as all the human beings on Earth, that in future where we are heading to, whether our fate is like Mars or it is like Venus. So are we going to be a greenhouse gas dominated planet, and therefore no life can thrive on such a planet? Or we are also going to see like a Martian kind of situations, driving up the planet slowly and losing the magnetosphere with of course due course of time. So these are very challenging prospects. ISRO is supporting all the what you call universities and academics to participate in their programs, and we have a strong presence through various public outreach programs. We have at Space Application Center, I can tell you there are certain things, some training programs for students, things called TREES. But we would love to see if any student after qualifying NET fellowship, basically, if they want to take planetary science as a career, then they are most welcome to
come to any of the planetary science institutes in India, including of course PRL is retained in that, and also State Education Center is continuously doing that. So once again, I would like to thank, and it is a great opportunity for me, being a student of geology, and to interact with my sirs after quite some time. Even though I would have to, I would have been much happier to sometimes visit in person, and I would like to invite each one of you, whenever you get some time, to come to Space Application Center Ahmedabad. We have a very good exhibitions also, it's the light. That's it. Thank you.
Thank you very much, Shatrughuda, for the invitation and all of you. Thank you so much.
And Nivedita, I have two observations.
Yes, sir.
Yeah. This for Ranjan, your talk was very nice, and it's a very good fundamental concept. I am not an expert on remote sensing. I am not an expert on remote sensing and GIS. However, I would like to know, normally we use digital library of hyperspectral curves to identify minerals, right? So how this fits into the natural specimens, which is a complex compositions?
Sorry, what was that? What was the last one?
How best this hyperspectral signatures fits for a natural specimens which is having a complex compositions?
Okay, so this like mostly for silicates, what you have, the molecules vibrate, the molecules rotate and turn, and also you have electrons that transit between different energy levels inside the atoms. So all of this have very unique absorptions and emissions at specific wavelengths. So these are like the DNA, you can say. You can like track which specimen it's coming from. So it's very like accurate also and effective, that you don't have to spend a lot of chemicals or anything for doing that chemical analysis. You can simply take a photo at different wavelengths, and based on the reflectances at different wavelengths, you can infer what process is going on, like crystal field transitions or molecular vibrations and rotations. And from that also you can easily deduce what sort of minerals is there. Sometimes you might not be able to tell which specific mineral is there, but what sort of group is present. For example, sulfate or a carbonate or a hydroxyl group, all those you can quite easily infer from the hyperspectral instruments.
Okay. So not all the individual mineral.
Yeah, sir.
For example,
Ranjanda.
not in the,
Yeah, Ranjanda, let me answer this. Sir, you are asking about the getting signatures of individual minerals from a complex rock by the hyperspectral data. No. So there are some process that are called linear or non-linear unmixed. Okay. There, what we do that we try to start with some spectra of individual minerals, and then try to mix them in proportion. That is calculated in mathematically. Okay, we just mixing not the samples, we are mixing the spectra and try to achieve the ultimate spectra that is we are getting from the rock itself. So by this mixing and unmixing methods, you could not you will get that 100% what pinpoint that these and these and these minerals are there, but you will get an idea to what are the constituent minerals. So you are getting a complex spectra, and then you can easily unmix it with certain physical and mathematical parameters to find the individual N members.
okay. So subsequently you will validate with the field sample analysis.
Yes, sir. That is must have been done. That is the basic key.
Yeah. Thank you.
Thank you, sir.
Any questions from students? Students, scholar?
Students, please ask questions. Any kind of question you may ask.
Nivedita di, I think we may conclude.
Okay, is there any, sorry, is there any advancement in using remote sensing to understand subsurface structures by extrapolating the surface structures?
Hello.
Is there any advancement in that?
May I come in? Are you interested in subsurface structure?
Yes, Jadavda, you can answer. Yeah.
Yeah, so it is possible. It is possible with very low frequency GPRs or ground penetrating radars. This kind of equipment you can put it in ground based platform, or you may keep it in a airborne platform. And these days, very high spaceborne GPS is also possible. In fact, there are two instruments on Mars. One is Sharad and the other one is Masis. So actually, the marks of this, they are basically very low frequency ground penetrating radars, spaceborne radars, and it can penetrate quite up to some layers underneath. And in fact, very nice work has come out on the polar layer deposits of Mars using this kind of ground penetrating radar. And at Space Acquisition Center, we developed our own ground penetrating radar. And in fact, one such ground penetrating radar will be flown both in ISRO-JAXA Lunar Polar Exploration Mission very recently. I mean, it will be flown in 2023-24 timeframe. And similar kind of an instrument is approved already for India's first lunar mission. And all these instruments are being built by Space Acquisition Center here in Ahmedabad. So yes, it is a very interesting tool, and the prospect is quite high once, if you are interested to look into the subsurface structures. But of course, there are certain limitations, and knowing those limitations, we need to analyze the data.
Thank you.
Thank you.
One question in the inbox. How to do flood assessment of a deltaic area in a planetary body using remote sensing?
Yeah, so to do okay, Shubham, you want to answer this?
No. I was referring to you.
Go ahead.
No, I was referring to you.
Okay. So what you do is you need the topographic data. From the topographic data, you have a series of procedures that you do to derive these the slope maps and the digital elevation models are like the flow lines and where the water will finally move to watershed area. All these delineations you do, and these if you want to do this by hand, it will be very difficult. So there are some algorithms which look for these. They will tell you where exactly the water would accumulate, and after you have all this data, then comes the interpretation part where you fix the boundaries and you decide what sort of water will whether it will accumulate or it will flow past that area, or whether it will not even flow into that direction. So all those you can do.
If we don't have any more question, I think we should conclude at this point. What do you think, Priyabrata?
I think. Hello, Priyabrata, are you there? I think you may say a few words here.
Yeah. The link will be available till 7 p.m. and we have to take some student feedback or vote of thanks. So,
yes.
Please say a few words and then we would conclude for the technical session.
Nivedita, I think Priyaprata's microphone is not working. So
Okay. Then you can
his,
say.
his internet, yes, his internet is gone. So
Oh. So
okay.
then
So,
you or Ranjan may.
yes, I will take the opportunity to
Okay.
like that. So first, we just want to, behalf of Priyaprata and Ranjanda, I want to thank you all to invite us and to patiently listen to us, to our presentations, our little effort here. So, and another thing, we just wanted to share there is a to mainly to the students, to the young students, that there are a vast opportunity ahead in the domain of planetary science. So as Shatadru already mentioned, I rather prefer Shatadru sir has already mentioned that in the domain of planetary, so people can come and join with um, in the domain of PhD research. So after completing their MSc in geology or physics rather, so they can join to work freely in planetary science, not only in remote sensing. What I am doing is purely the field-based geological analysis, and that is mainly termed as the analog studies, which is also a very interesting branch of planetary science also. So there are a good opportunity in research domain, and also it's a good career opportunity. Many private organizations that are now coming forward to do space research and space explorations, that are taking freshers as workers. So this is a good domain to work on after completing your masters. And another thing I want to share that from on behalf of with free, we would like to get a student feedback form, so that will be shared via you, Nivedita. So we can just you just make them fill it up and you can send to us.
Okay. I will send with their certificates and they will send you the feedback.
Okay. Thank you. That's all.
Thank you very much to all of our resource person. It was a wonderful experience for us. I would now likely to approach our students if they like to give some feedback on this workshop. Any of you, if you are interested, then you can say something.
I want to say something.
Introduce yourself.
Myself, Saurin Mairi, first year from BSc undergraduate in geology from KJDC College.
Okay.
At first, I want to thank our respected professors and thanks to our KJDC college members for arranging this knowledgeable workshop. From this workshop, I had gathered knowledge about fundamentals of planetary sciences. It shows how principles and equations learned in introductory geology classes can be applied to study many aspects of planets, including dynamics, surfaces, and interiors. It also includes the discovery and characterizations of extrasolar planets. I am very much interested in that type of future works. At last, I want to thanks to everyone for your kind attention. It will be a remarkable seminar. I will like to request KJDC College to keep arranging this type of seminar afterwards.
Okay, thank you very much, Shorin. Anyone else?
I want to share something.
Please introduce yourself.
Good evening, everyone. I'm Apurva Dev, student of second year from the Department of Geology. I would like to share a few words regarding my experience on attending the workshop. We got to know about the planetary environment within which the planets were formed, how they have reacted and interacted, especially of the planet Mars, I would rather say. The satellite images that we have seen were really amazing. Like we have never seen any such image before anywhere in internet, and we also got to know about the recent planetary missions that are going on and the development of new techniques that are giving better insights of the solar system. Overall, it was an amazing experience attending the workshop as we got to know so much about the solar system and things associated with it. And I would rather say the knowledge that we have gathered from this workshop will definitely help us in our future studies. And lastly, I would like to express my earnest gratitude and thankfulness to all the speakers. Thank you, everyone.
Thank you very much, Apurva. And now I would like to invite our final semester student, Orpita Pandey, to give the vote of thanks. Orpita, are you here?
Yes, ma'am. Am I audible?
Yeah, perfectly audible. Please go on.
Okay. Thank you, ma'am. Good evening, everyone. Respected OIC sir, HOD sir, other teachers and honorable resource person and all the participants. It is such an honor for me to get the opportunity to thank you all dignitaries. Myself, Orpita Pandey, student of 6th semester, Department of Geology of this college. I would like to express my gratitude to all the esteemed delegates and participants of the workshop for their presence and contribution to make this event a great success. During this one-day international online workshop on the fundamental of planetary science, we got an overview on certain research method, technique, application, and most importantly, the future career scopes in this highly prospecting research field. I extend my sincere gratitude to our respected officer in charge, Professor Kumar Das sir, for his support and cooperation. I express the earnest thankfulness to our respected head of department, Dr. Ashish Kumar Maji sir, for his involvement and encouragement. I express my great thankfulness to our honorable resource persons, Dr. Priyabroto Dash, Dr. Ranjan Sharkar and Mr. Shubham Sharkar for taking out time from their busy schedule to grace the event with such valuable information. I extend my warm gratitude to our beloved Nivedita ma'am and Indari ma'am, professors of our department for organizing such an impactful workshop. I must thank to all the participants, teachers and students from our department and the non-teaching members of our college for their enthusiastic attendance. And lastly, my heartfelt thanks to my batchmates, juniors and all the dedicated persons from the different organization and institution within and outside India for their active participation. Thank you everyone once again for making it a great success. Thank you very much. Have a nice day.
Thank you.